Hi everyone, I'm Xingyun Chen. This is a recording of the 10th exam preparation section. As always, if you have any questions, feel free to come to my office hours. It is 3 to 5 p.m. every Thursday. And also, if you have any comments about my exam preparation section or my office hours, feel free to fill in this anonymous feedback form and the links provided on the slides. So let's get started. For this week, we will have two questions about machine learning algorithms. The first question is about decision trees, and the second question is about perceptrons. So let's get started. For the first question, it asks us to build a decision tree given this data set in the table. So for each point in this data set, it has three binary features, A, B, C. So basically, these features will take the values of either 0 or 1. And each point is also assigned with a label. So the label is also binary. It could take the values of plus or minus. So in the first part of the question, we will build this decision tree by greatly splitting according to information again. So basically, it means that for each feature we use to do the split, we want to maximize the information again for the label assignment. Then in the first part of question, it asks about which features could be at the root of the resulting tree, which means that which features should we use to do our first split. So before we start with the question, let's review some important concepts first. So the first concept is about the entropy. So for a random variable y, suppose we know all the possible values that could be assigned to these variables and the probabilities of assigning this random variable to different values, then the entropy term will be the sum of the probability of each value times a log of this probability. And here the log has the base of 2. Once we sum over all these terms and we do a negation, we get our entropy value. At the high level, the entropy of a random variable will be high if the probability is kind of uniformly distributed among all the possible values, and the entropy will be low if the probability distribution is more deterministic or more skewed. For example, here, suppose this random variable y means the label of our data set, which could take the values of either plus or minus. Then assume that the probability of y equals to plus is 1, so which means that the probability of y equals to minus becomes 0. Then in this case, if we compute this term, we will see that the entropy will be 0. This is the minimum entropy we could get for a random variable. On the other hand, suppose the probability of y equals to each label is 0.5, then our entropy term becomes 1, which is the maximum value of the entropy we can get. So with this definition of entropy, what do we mean by information again? So suppose we are also given the value of x. So related to the decision tree, it means that we are going to do a split at the feature x. Then the information again given x becomes the entropy of y minus the entropy of y given x. So for this specific question, here x could be A, B, or C. Then if we want to maximize the information again, it means that we want to minimize the entropy of y given x for all these features. So how should we compute the entropy of y given x for any feature? Let's take the feature A as an example. So basically, the entropy of y given A is equal to the probability of A equals to 0 times the entropy of y given A equals to 0, plus the probability of A equals to 1 times the entropy of y given A equals to 1. Then we are trying to like kind of expand these formulas. So for the so basically to expand the first term, the probability of y given a equals to 0. So we can see that basically this term will be a minus of this expanded term. And if we compare this formula with the definition of the entropy term Hy here, we can see that the main difference is that we basically replace this probability of y with the conditional probability of y given a equals to 0. So this is how we can compute the entropy term given us the value of a certain variable. And similarly, to compute the entropy of y given a equals to 1, we will replace this probability of y with the conditional probability of y given a equals to 1. Then summing over these terms, we could get the entropy of 0.881, so which is roughly the entropy up of y given a after we do the first split. Similarly, we can compute that the entropy of y given c is also 0.81, and the entropy of y given b is 1. Therefore, the root we should select should be either A or C. So how could we like intuitively interpret these results? So for example, if we are not going to compute the concrete values, how could we know that if we want to maximize information gain, we need to split over A or C? Then here is the reason. So suppose we are going to split at A first, then we can see that if we like take a look at all the points with A equals to 0, then we see that there are like 0.75 of probability that the label will be plus, and there is like 0.25 of the probability that the label will be minus. And so, if we take a look at the points where A equals to 1, we can see that also for 75% of the points, they will be a minus, and 25% of points, it will be a plus. So this means that if we do a split over the A, then basically we will see that the distributions of different labels will be like more skewed towards one label in each split, which is helpful if you want to like kind of assign the labels in the end. So similarly, if we want to do this split over C, still we can see that if we take a look at the C equals to 0, 0, 0, 0, then we will see that also when the values of C is equals to 0, there will be that 75% that the labels will be plus. So if we compare these two probabilities, we can easily infer that splitting over A and C will be equally good. However, if we do the first split over B, and we take a look at the points given at B equals to 0, we will see that still in this split, there will be like 50% of the labels with 50% of the points with the label plus and 50% of points with the label minus, which means that when we do the first split over B, it doesn't like give more information about how likely the label will be assigned to a specific point. So this is why if we want to kind of build this decision tree by like greatly maximizing the information gain per each split, then it is better to select A or C as the root of the decision tree. Okay, then the second part of the question is asking that if we do these splits by gradually maximizing the information gain per split, then how many edges are there in the longest path of the resulting tree? So basically, in this tree, we are already saying that we will have either A or C as the root. But then here, basically, the question is like, so we already know that if we know the values of all these features, definitely we will we will kind of know the label of a certain data point. Then basically here, by asking about like the number of edges, it is more about like could we kind of determine the label with by knowing a small number of features. So basically here, let's take A as an example. Suppose we do the first split over A, then we will kind of see that in order to determine the label, we will need to do two other splits over B or C, because if we only do one split over B or one split over C, still we cannot decide the label, because there's always some cases where the two points have the same value of B or C, but their labels are different. Therefore, in this case, we need to know the values of all three features. So basically, the longest path will have three edges to enumerate all these features. And similarly, if we do the first split over C, it will always be the same case. Then, basically, in the second part of the question, it asks us to build a decision tree with the smallest possible height. So basically, here we do not need to like unnecessarily maximize the information again per split. So similarly, the question is asked about like what should be the root of the tree, and also how many edges are there. So by smallest possible height, it basically asks us like if we can kind of decrease the number of edges in the longest path. And in the first part of the question, we already see that when we select A or C as the root, we will get the longest path with three edges. Then for this part, we are basically asking if we choose, if we build a tree in another way, whether we could actually get a decision tree with a smaller height. So basically, here we will consider the only remaining case, which means that we will use B as the root. So let's do it. So basically, suppose we will choose B, and then basically, for the B, there are like so when B is equals to 0, there are like these 4 points, right? Then actually, if we take a look, so even if we discussed it in previous part, so if we do the first split over B, the information again for that split is 0, because the probabilities of assigning two different labels in the same split is still 50%. However, the good thing is that if we start with the B as the root, so actually we only need to know a single second feature in order to determine the label. The reason is that here, basically you can see that when we have B equals to 0, and we know that for the first two data points, A equals to 0, and for the second, for like the third and the fourth data points, A is equals to 1, and we can like see that when B is equals to 0, we only need to know the value of A in order to decide the label, because we can see that in the first top part of the table, where A is equals to 0, then the labels are plus, in the bottom part, when the A is equals to 1, then the label is minus. So this is the case when B is equals to 0. Then when B is equals to 1, so which means that at least 4 points. Then again, we will see that well, for all these like points with plus, all of them have C equals to 0. And when a label is minus, C is equals to 1. So again, for the second part, when B is equals to 1, we only need to know the label of C in order to decide the label of data points. Therefore, when we build the decision tree this way, the height of the decision tree becomes 2, which is smaller than 3. Therefore, if we want to build a decision tree with the smallest possible height, then we should assign B to be the root. And also, in this case, the longest path becomes 2. So basically, the takeaway here is that if we do the build the decision tree by greatly maximize the information per split, it does not always result in the optimal decision tree if we are considering the size of the final decision tree. So here basically in this question we are provided with a counterexample. And then for part B, it is kind of a very pretty fun question. It is about building the decision tree ourselves. So basically here we have points from 2 classes shown as plus and dots. Then there are some requirements when we are building the decision tree. So firstly, as we can see from these figures, we are asked to draw the decision tree of depths at most 2 that can separate all these given data. And for all these predicates, they need to be binary and only involve the thresholding of a single variable. So basically, we can see there are 2 variables here. One is f1 in the x-axis, one is f2 in the y-axis, and and also if the tree is kind of finalized in the after one split, and we don't need to do more redundant splits. And also when we are trying to complete the decision tree, we will also draw the corresponding decision boundaries on the scatter plot. Okay, so let's take a look at the first question. So basically here we can see that the plus and the dots are nicely separated. So it is pretty easy to see that for all these plus, they have all of them have an f1 smaller than 1. Therefore, we can do the first split in this way. So basically, we will do that. Basically, the first split is f1 is smaller than 1. And if the answer is no, we can see that all these points to the right of these decision boundaries are dots. So we can already see that when it is a no, it is dot. Then when it is yes, we can also see that for all these for all these plus, they also have f2 smaller than 1. Therefore, we can have another split over f2. So this is f2 smaller than 1. We can see that if it is yes, then all of them are plus, or otherwise they are dot. So this is the first decision tree. Then what about the second decision tree? So basically, from this decision tree chart, we can see that if a data set could be separated with this format of decision tree, then it means that it should be separable by 4 rectangles, and also each of these rectangles should be like parallel to the x and y axis. So here we can do some like initial attempts. So for example, here we want to separate the plus and dots. Then first we can try to like split over F1. So suppose we draw this like line of F1 equals to 1, then we can kind of assume that for the like then we can see that for all of these like dots, they will have F1 at least not smaller than 1. So we can see that in the left part of this like decision boundaries, all of them are like a plus. Then we need to do more separations for the right part. Then suppose we are going to do the separation over the F2. Here we can do like F2 like smaller than minus 0.5. Then we can see that if for all the points like below these decision trees, they will be plus. However, for the points above the decision boundary, there are still like both plus and dot. So which means that it could this like a separation could not be finished with like only like with a decision tree of depth 2, but definitely it could be separable with like a deeper decision trees. Therefore, for this question, the answer is that we cannot do it with this decision tree. Then let's take a look at the third decision tree. So actually, although like this scatter plots seem like pretty complicated, it is separable with like this decision tree. So first, let's do a split over F2 here. Then we can see that for the when we do the F2, there will be when F2 is smaller than 0, there will the points of plus and dots could be nicely separable by F1. Here, if we draw a decision boundary of F1 equals to -2, then when the points are to the left of this decision boundary, they are plus, otherwise they are dot. And for the points where F2 is greater than 0, again, we can draw a decision boundary given F1 equals to 2. Then if F1 is smaller than 2, it will be dot, otherwise it will be a plus. So basically, we can see that all these like points could be separated by like 4 rectangles. Then question 2 is about perceptron. So the idea here is that we will have several points. They will have in the forms of S1, X2, and each of them will be assigned with a label. And these are binary labels. They could take the values of dots or cross. So for these questions, it asks like given these different sets of features, whether all these points could be like perfectly separated by a perceptron. So again, let's review the concept first. So for perceptron, basically we are going to learn a linear model taking the value of x. So basically here, x simply means all the set of features are listed here. Then basically we will learn a weights for each of these x. So this will be our like perceptron model, and we will so basically with this decision boundary, if it's if the value of w multiplied by x is not smaller than 0, then we will assign a label of 1, and also the prediction will be 0 or -1 here when this when their product is smaller than 0. So this is the formula of the perception. So basically, the idea here is that if we are only given the features listed on the program description, we are only allowed to have linear combinations of them, whether they could kind of represent the decision boundary of these points. So let's do some more derivation and plots to check each option. So let's take a look at each of these plots. So in the first case, these points are pretty easy to separate because actually we only need to know the x1 value, and also actually the decision boundary could just be x1 equals to 0. So basically, when x1 is smaller than 0, it will be cross. Otherwise, when x1 is greater than 0, it could be dot. So in this way, so basically we can just have once we have x1 in the feature, it is enough to perfectly classify the data. So the answer is all these choices are correct. Then in the second case, we will see that so if the features only include x1, x2, then it means that the decision boundary needs to pass the origin, and also it has to be a line. Then we will see that this will not be sufficient to classify this data. So the reason is if we want to have a line passing the origin, basically there will always be one side to a decision boundary where the points of two labels exist at the same time. So basically, this option is not possible. Then if we are also given 1 as the feature, then basically it means that still the decision boundary needs to be a straight line, but this time it doesn't need to pass the origin. It could be off. But again, we will see that it will not be sufficient to to classify these points, because basically in this case we need something like this to separate these points of different labels. So the first choice is not valid. So specifically, why do we need this? Because basically for these two sets of points, they have these properties. So basically, comparing the points of these two labels. So for dots, they have they have a smaller absolute value of x1, but higher x2 compared to crosses. So therefore, if we include x1 square as its feature, that enables us to draw something draw a decision boundary like this. Then, so in this way, we will be able to separate the data points of these two labels. Then if we include the absolute value of x1 as the feature, then basically it means that our decision boundaries can be like this. Then we can see that it also enables us to classify this data. So this is also a valid choice. Then in the fourth option, note that we also include the ground truth stable as a feature. Then given y, definitely we will be able to perfectly classify y, because in this case we only need y as a feature to do the prediction, since we already know it. So definitely this choice will be always selected for all the cases with different positions of these points. Then let's move on to the third case. So if the for the last choice, if the decision boundary needs to pass the origin and it has to be linear, it is we will say it is impossible. Basically, let's say if you want to draw this decision boundary, then basically there will again some points will always be on like so the for both sides of the decision boundary there will still be points of different labels, and they could even be like on for both of them could even be on the decision boundary. So this choice is not valid. Then yeah, similarly, if we add the ground truth label y, then this is then it will be able to classify the data because y is the only thing we need to know. So this time to separate these points of two labels, uh, actually we only need to know the value of x1 if we don't need to leave this like decision boundary to pass the origin. So basically, when the x1 is like, greater than this like a threshold, which means that they are like to the right of the decision boundary, then they are dots. Otherwise, they are crosses. So basically, it means that if we are also allows like the points to like so that it does not need to pass the origin, then the first choice is also correct. Notice that in this data set, because all the x1s are greater than 0, which means that the actual value of x1 is equal to x1, then since knowing x1 and x2 alone is not sufficient, this means that knowing actual value of x1 is also not helpful. So this is not a correct choice. Then let's see whether including like the x1 square will help. So actually, if we have the square of x1, it will enable a decision boundary like this. So it could be something like this. So this decision boundary still passes the origin, but basically it does not need to be a straight line. So this is why it could also kind of classify these two sets of points where one set has a larger x1 and another set has a smaller x1. So basically means that the second choice is also it is also like sufficient to classify this data. That's it. Thank you. If you have more questions, feel free to come to my office hours.